Hi, welcome back. In the last video, we actually stopped at the Bernoulli's equation in our analysis of a pipe flow. Alright, so now, since we have done the energy balance, which is essentially the Bernoulli's equation, we want to relate this velocity to this velocity here. Alright, let's just shuffle the terms around. PC minus PVC over rho equals to V of the vena contractor squared over 2 minus V of the cross-sectional area squared over 2. Square it over 2. Alright, so next we need to relate these two, try and eliminate some terms. Well, we can do that actually by using the continuity equation, which is essentially a mass balance equation. So usually we have mass balance, energy balance, and momentum balance for fluids. Alright, so this is the mass balance, which says that mass in equals to mass out. Simple as that. So what's that mass? We'll have rho A U in equals the rho A U out. Since we have a constant density, we can just assume that the volumetric flow rate in equals the volumetric flow rate out. A times U. Now let's just substitute all these values in. VC and C, and since we know AC and area of the orifice, we can just plug that into our equation as well. So AC times VC, V bar of C, equals to A of the vena contractor times velocity at the vena contractor. So that is actually just 0.63 times of the area of the orifice. If you want to know how that is done, you got to go and see the experiments of how they actually determine this. Excuse me. This is actually a vena contractor constant for sharp edge orifice, which we assume for this case the orifice is sharp. Right? So A orifice times 0.63 times V of the vena contractor area, VVC. Next step, we want to make VVC the subject, because what we want to do is get rid of this. Right, so VVC equals to A of the cross-sectional area times 0.63 A orifice, that times VC. Alright, so now let's put this back into our equation here. So we have PC minus PVC over rho equals to half VC squared times AC over 0.63 times of area of the orifice whole thing squared. Remember that V of VC is actually AC over 0.63 times A orifice times VC. You square both sides, you have to square this constant as well. And you subtract VVC squared at the back. And let's take the common term out. Half VVC squared times AC over 0.63 A orifice squared minus 1, and that will be the expression for pressure drop before entering the turbulence region. Now, since we already have derived our equation for the pressure drop, now we need another equation for this little area, the turbulence zone. And now we can't use the Bernoulli's equation anymore because the pressure drop, the shear stress and the head loss is not negligible anymore. And hence we need to take a look at our control volume a little closer. We have a pipe flow here. Alright. Okay, so the fluid's coming in here, it's converging. I'm not going to draw the streamlines because it will be very messy. It will be very messy, sorry. The streamlines will actually converge here in the vena contractor and they'll start expanding. And there'll be some turbulence. I don't know how much. And our control volume will be here all the way out to here. The control volume will be such that here we'll have a re-established flow, and by continuity equation we know that the flow rate here equals to the flow rate here, and the pressure here will be P infinity, and then there'll be a there'll be a pressure drop here. So we have a P infinity here and the stagnation pressure here. Alright, so what we need to know now is how the momentum is actually acting on the system. Because you see, we don't know the head loss term in this system due to the turbulence, but we can infer that from momentum balance that since this area of turbulence isn't moving, the forces this way and the forces this way must balance. So you can think of it as an inelastic collision where momentum is still conserved but there's energy lost. Alright, so let's do our momentum balance equation. The change in momentum in the system equals to the sum of force acting on this system plus the force due to the momentum flows going into the system minus the force due to the momentum or the mass flow rates leaving the system. Okay, this is a steady state problem, so we just neglect anything that changes with time. We assume that to be 0. So thus we have the sum of force on the system equals to sum of M out, U out, minus sum M in, U in. Alright, so for this case it's quite simple what the flow rates in and out are. It's just one flow rate in here and one flow rate out, and that's the same mass. So let's just replace the right hand side with a common mass flow rate term, and here we will have a velocity again. And what will that velocity be? Since here we have a velocity Vc, by continuity equation the density doesn't change, so the volumetric flow rate in and the volumetric flow rate out here must be the same. So if it enters at Vc, it must exit at Vc as well. So the velocity exiting will be Vc, and the other thing is that, okay, what's the velocity going in? You can see this control volume will be exactly at the vena contractor. In reality we don't know where it is, but never mind, that's not important. We just focus on the theoretical place where the vena contractor is. We see that the velocity is actually VVC, which is actually just over here, VVC, velocity at the vena contractor area. Alright. Next thing we need to know is the force acting on this system. We know the pressure here is just P infinity, and that's acting to the left. So let's just have a negative sign. P infinity times the area C. This is the free stream pressure, or the pressure at the second part here. Now the more troublesome thing is what this pressure is over here. Here we have some turbulence, so the pressure variations are, all over the place. But there's something we can do to actually try and analyze the problem. Now let's just take a look at that turbulent area just after the orifice plate. Alright. So let me use red. Okay. Now we know for one thing, pressure here is just PVC. Okay? PVC. We can actually just derive that from our Bernoulli's equation. What do we know here? In this area here, we note that it isn't moving on average. I mean, there's some turbulence going on in there, but the turbulence is just there. It's not moving from here to here or here to here. And from that we must conclude that this thing is, as a whole, not including the fluid that's inside, but as a whole, it is stationary. So that the force acting on this system, net force acting on this system, is 0. Likewise for the little bit of turbulence over here, we also conclude that the net force acting on it is 0. Now, what are the forces acting on this system? We have some area here, and we have the pressure that's acting on this area. That will exert a force going upwards. Alright? And we know that there will be some normal contact forces acting downwards, and likewise from the left as well. So we know from the right, okay, can't see it very well, but from the right, there's some force acting here and there's some force acting in this direction. So what are the forces acting? Let's enlarge this. Let's imagine a square or a little rectangle. There's P infinity acting in this way. There's a boundary here and a boundary here. And what is this pressure? We are not that sure what the pressure is, but let's take a look at this for a moment. What does this look like to you? Imagine if we actually extend the length P question mark, we don't know what that is, P infinity into there. This looks like a bit like a manometer or something like that. Now if we shorten the pipe so much, let's say we shorten it from here to here, and then we just neglect all this, and then let's shorten it some more. What you have is just this P infinity here, this P question mark. What you have when you shorten this so-called manometer short enough, you will get this system. And from this so-called manometer, you know that if the fluid inside is not moving, then the pressure here is equals to the pressure here. No matter what the fluid inside is doing, it's just not moving in or out of the pipe. So if that's the case, this P question mark equals to P infinity. Now it's the same whether this pipe is very long or so-called very short, until like there's like nothing there. There's like no pipe area at all. So this will just be equal to P infinity. Of course, over here you have whatever normal contact forces you need to have, but on the whole this is P infinity. And by Newton's third law, if the force here is P infinity, then the force by this volume, or the pressure by this volume here, is also P infinity. Alright? Now once you do that, you can kind of safely say that P infinity is acting on this entire control volume in this direction, in this manner. Because you see that over here there's P infinity acting. There's P infinity acting into this control volume, and this control volume is pushing against this area with a pressure P infinity as well. So effectively this whole area is getting acted upon by P infinity, or the free stream pressure, or PVC rather, sorry, it should be PVC. PVC, or P infinity. VC. Alright, the pressure of the vena contractor area is just acting on this whole system like that. So PVC minus, or times AC minus P infinity, PVC AC minus P infinity times AC is equal to this. Now let's make it a little easier by rearranging our equation into this form. AC rho Alright, now we have done this. Okay, how did we get from here to here? What we did is bring this AC over here and divide the entire equation by the density. So that's what we are doing here. Alright. Next thing we do, what's this mass flow rate? Mass flow rate is just density times volume. Density times whatever volume. What's the volumetric flow rate? Here we have conveniently put AC times V at the cross-sectional area. So it's just VC. AC times rho. Just to remind you what VC is, this is the area AC. This is VC. Okay? Now these terms can cancel. Alright, and that will just equal VC as VC minus V of VC. Oh my goodness, it's bad lettering, but okay. This is the velocity at the cross-sectional area. This is at the vena contractor. Now let's see how they relate again. We want to eliminate this V of the vena contractor. So what we do is simply substitute this into this equation. So that is simply VVC minus, or times VVC minus AC over 0.63 A orifice times V C. Let's take the common term out, and we'll have something like this. Okay? Hopefully by the next video we can actually complete the derivation, but that's all we have for now. Stay tuned and thanks for watching. Please subscribe, rate and comment.